716. A small weight is suspended from a string of negligible weight and given an initial horizontal velocity of 2 meters per second with the string initially vertical. Find the maximum angle theta that the string makes with the vertical if the string is 1 meter long. Alright, so here's a sketch. So we start with the string initially vertical, and the mass has an initial velocity v sub I, and then the mass swings up to some unknown maximum angle theta. And to solve this problem, we're going to use conservation of mechanical energy. So from a very top-level standpoint, let's start by defining the reference line for gravitational potential energy. So that's my zero reference line. And so initially, all of the energy is kinetic. And what happens is the string swings up along the arc here is it gains height, which means it gains gravitational potential energy, and it will keep gaining it until it loses all of its kinetic energy, at which point it will get to its maximum angle. So that's the big idea here. And so let the length of the string be L. And I can project that length L onto here and conclude that this length is L times cosine theta. And so clearly L, which is this distance, L minus L cosine theta is equal to h. That's the distance it swings up. So L minus L cosine theta is equal to h. Okay, so the kinetic energy initial plus the gravitational potential energy initial is equal to the kinetic energy final plus the gravitational potential energy final. Kinetic energy initial is 1/2 VI squared. With my choice for the zero reference there, there's no joule contribution here. So plus 0 joules is equal to the final kinetic energy. Okay, the final kinetic energy is 0 joules. There's no speed when it gets to the maximum angle. All of the kinetic energy has been changed into gravitational potential energy. So the gravitational potential energy is mgh, and so essentially, since h is this, it's mg times L minus L cosine theta. Okay. So you can see these two terms cancel out, and so therefore the m's are going to cancel on both sides. The answer here is independent of mass. I can factor an L out here, and so essentially the right-hand side is equal to GL times 1 minus cosine theta. And then after canceling this, I get 1/2 VI squared. It's perhaps nice to multiply through by 2 just to clear this of fractions, and if you do that, then this disappears from there and pops up over here. So let me divide both sides by 2GL, and I get VI squared over 2GL is equal to 1 minus cosine theta. Well, that means that cosine theta is equal to 1 minus VI squared over 2GL. And finally, theta, which is what I want, is the arc cosine of that. So it's cosine minus 1 minus pi squared over 2 GL. And so if you put the numbers in, cosine minus 1 of 1 minus 2 meters per second is the initial horizontal velocity squared divided by 2 times, I'm going to use a g of 10 meters per second times L, 1 meter. Use square brackets here just to make things a little bit cleaner. Okay, so quickly a unit check. So I've got meters squared per second squared in the numerator, and I have meters squared per second squared in the denominator, and I get something that's dimensionless. Had to be, because 1 is dimensionless and an angle is dimensionless. And so if you put this through your calculator, you should get something that's approximately equal to 37 degrees.